All right, let's take a look at our practice test. For the instructions, we're asked to solve each word problem. For the first problem, we have that a satellite traveling in a circular orbit 1,600,000 meters above the surface of the Earth takes 7,200 seconds to complete an orbit. If the radius of the Earth is approximately 6,400,000 meters, what is the linear speed of the satellite in kilometers per hour? We're asked to round your answer to the nearest tenth. Okay, so for the first problem, I'm just going to go a little bit slower. I'm just going to recap all the things we talked about in the lesson. So first off, let me go back up for a second. We are specifically asked to find the linear speed of the satellite in kilometers per hour. So what exactly do we mean by linear speed? Well, recall in the lesson we talked about our distance formula, what we use for motion word problems. So we had that distance is equal to rate times time, and we just solved it for the rate. So basically we divide both sides by t, and we end up with rate is equal to your distance divided by your time. So the formula we use is very similar. Instead of the R for rate, we use V, which is going to stand for your linear speed. And this is equal to, instead of D for distance, because we're going around a circle, right? We think about that as the arc length. So we use S for arc length over your T, which is your time. Okay. Now, just to think about this with a simple example, let's suppose that we go here, and this is just not related to the problem. It's just so we understand the concept. Let's say we trace an arc like this, and I just say that this is 10 meters, for example. So this is the problem we're in currently. It says it's 10 meters. That's your arc length S. Okay. So your linear speed is equal to 10 meters, and I'll just abbreviate meters, over whatever time they give you. Let's just say it was 2 seconds. So down here, this would say 2 seconds. And basically, you would simplify this into a unit rate. So you would say this is 5 meters per 1 second, right? So you'd write it like this, or 5 meters per second like this. Whatever your book tells you to do. Some teachers have a preference for this, others this. It just depends. So this is the basic concept behind linear speed. Now, in most cases, you are not given this information directly. You have to go through a series of steps to get everything right. And a lot of times you have to convert a lot of different units. So let's start off with something else, which is the angular speed. So this is denoted with the Greek letter omega. And I know that's not a perfect drawing of that symbol, but it's the best I can do. So this is equal to your theta, which is in radians, over your t, which is your time. Okay, so real easy to remember this one. Now, these two are going to be related because remember this S, this arc length, we talked about the fact that this is your R, your radius, times your theta, which is your angle measured in radians. So you could say that this is R times theta over t, and then of course you could break this up into R times theta over t, and this ends up giving you, let me slide this down just a little bit, you could take this omega here, which is your theta over t, and just multiply it by r, your radius. So if you have your angular speed, then all you have to do is multiply by the radius, and you found your linear speed. So let's go back up to the problem, and let's think about the angular speed first. So we're just thinking about this orbit part, where it says that it takes 7,200 seconds to complete an orbit. Well, what do we mean by an orbit? Well, that means that this satellite is going around like this, right? So if it goes around once, that's one complete revolution or one complete rotation. And with a circle, in terms of radians, that's going to be an angle that's 2 pi. So for this part right here, I can just put in 2 pi. And then for the time, I can put in 7,200, and this is going to be in terms of seconds. Let me move this down just a little bit here. Now, here comes the tricky part. You usually have to do some sort of unit conversion. And in this case, we want to end up with kilometers per hour. Now, you can go through and multiply everything in one step. Some people do that. But for myself, it creates this really, really long chain. So I like to just do things one step at a time. So I'm just going to convert this over right now into hours. And if you think about the relationship between seconds and hours, well, there's going to be 60 seconds in 1 minute. And then there's going to be 60 minutes in 1 hour. So I could say that 1 hour is going to be equal to 3,600 seconds. And just using that to set up a little unit fraction, remember the value here is going to be 1, so we're just using it to cancel units. I'm going to put 3,600 seconds in the numerator, and I'm going to put 1 hour in the denominator. And the reason I do that is so seconds will cancel away. So those units are gone. And then here you're going to notice that this works out quite nicely. 2 times 3600 is 7200. So essentially this times this will cancel with this. So you're just left with pi radians per hour. Okay, so let me get rid of all this. I'm just going to write this a little bit more neatly. So you could write it like this. You could say pi over 1 hour. And you can leave the radians off. I think it's pretty obvious. Or you could say pi radians per hour like this. Whatever you want to do. Okay, so now that we understand that part, remember, if we want to get the linear speed, all we have to do is multiply this by the radius. Let me actually slide this down. And I'm just going to throw this in here. This pi over 1 hour. And all I have to do is multiply by the radius. Now, it's a little bit tricky. That's why I drew this picture. If you go back up, you'll see that the satellite is traveling in a circular orbit, and it's 1,600,000 meters above the surface of the Earth. Okay, well, here's the surface of the Earth, so it's above that by 1,600,000 meters. But you also have to take into account from right here, which is the center, going all the way up to the top part right there, that's going to give us a radius of 6,400,000 meters. So we have to add these two guys together to get the radius of this bigger circle here, which is the path that my satellite is following. Okay, so what I want to do is add those two together, and that would give me 8 million meters. Now, before I go through and just multiply this by 8 million meters, again, I think it's better just to convert it because we want to end up with kilometers. Right? If you come back up, you need kilometers per hour. This right now would give me meters per hour, so I don't want that. Let me actually get rid of this. I don't think we need this anymore. So let me say that I want 8 million meters times, there would be 1,000 meters in 1 kilometer. You could also use your metric prefix chart. You're just going to move this decimal point 3 places to the left. You could do it that way if you want. It's really up to you. So I'm just going to put this as 1 kilometer up here and then 1,000 meters down here. Can get rid of this. So you can see that the units here are going to cancel. And basically, you're just going to delete 3 zeros if you're dividing by 1,000 or move the decimal point 3 places to the left. So this gives me 8,000 kilometers or kilometers, as some people say. Let me get rid of this and I'll say 8,000. So 8,000 kilometers. And essentially what you end up with is 8,000 pi kilometers per hour. Okay, so that's what it is. Now it asked us to round this to the nearest tenth. So let's go ahead and punch this into the calculator. And when I do 8,000 times pi, I get about 25,132 let's go 741. Now we're rounding to the nearest tenth, so let's go 0.7, and you can cut these off. So this would be in terms of kilometers per hour. Okay, so let's grab this, and I'll just paste this in here. You can make a sentence if you want. I think it's unnecessary. So again, we're just answering the question, what is the linear speed of the satellite in kilometers per hour? Well, it's going to be approximately 25,132.7 kilometers per hour. All right, for problem 2, we're going to see that a local shop has a machine with a pulley of radius 0.1296 meters. If it takes 36 seconds for 112 centimeters of belt to go around the pulley, what is the angular speed of the pulley in radians per second? Now, I have here that we want to round your answer to the nearest hundredth, and I give you a little hint. Recall that theta, which is your angle measured in radians, is s, which is your arc length, divided by r, which is your radius. Then I have also give the linear speed of the belt in centimeters per second. We want to round your answer to the nearest tenth. So let me highlight what we're trying to find. We want to find the angular speed of the pulley in radians per second. And we also want to find or give the linear speed of the belt in centimeters per second. Let's go down here and think about what's going on with a little picture. So you have this belt that's traveling around this pulley here. And when we think about the linear speed in terms of the belt, it's going to be the same as that of a point on the circumference of the pulley. Okay, so what we're saying is that if we think about this belt traveling around the pulley, you're going to have 112 centimeters of this guy that's going to pass or travel around this pulley in 36 seconds. So you can use that to get your linear speed right away if you want to, and then you can use that to get your angular speed, or you can do it in a different order. There's a lot of ways to solve the problem. So let's just start with linear speed. So V is equal to your arc length, or the distance traveled around the circle here, is going to be 112 centimeters. So you could write that off to the side and say S is equal to 112 centimeters. And this would be over your time. So this is going to be 36 seconds. So if you punch that into your calculator, you're going to get approximately 3.1, and this would be in terms of centimeters per second. So that's your linear speed. You can just go ahead and answer that now. So let's just go ahead and say that V is approximately 3.1 centimeters per second. Now for the angular speed, you can do this in a few different ways. You could start off by saying that omega is equal to your theta divided by your t, right? Your theta divided by your time. So we know the time is going to be 36 seconds. So you could put that in there. And then in terms of your arc length, we know that it's 112 centimeters. So this is your S. And your R, your radius, is 0.1296 meters. But for this to work, we want the meters to be converted over to centimeters, or you can convert centimeters over to meters. I think this is probably easier to convert over. So I'm just going to move the decimal point 2 places to the right. So this would be 12.96 centimeters. And so the units here would cancel. So theta would be equal to this. And so 112 divided by 12.96, that's going to be approximately 8.64. So this is approximately 8.64. And this is just giving me my theta, right? My angle in terms of radians. You would need to divide it by 36 seconds to get your radians per second. Okay. Now you can actually use this approximation here. It's not really going to change your answer. If you wanted to put this in first and then divide by 36, you could do that. It would be a little bit more accurate, but we're rounding to the nearest hundredth, so it'll be okay. So we'll put this as approximately 8.64, and this is in terms of radians. Let me get rid of this. And then you can just do the division on your calculator, and I get exactly 0.24, but keep in mind this is still an approximation. So this is going to be 0.24 radians per second. So coming back here, I'm just going to put that omega, which is your angular speed, is going to be 0.24 radians per second. All right, let's take a look at problem number 3 now. So we have that a wind turbine blade with radius 35 feet makes 360 revolutions per hour. We want to find the linear speed in feet per minute of the wind turbine blade. Round your answer to the nearest tenth. Okay, so it's not necessary, but I did draw a little image for us here, just in case you're struggling with this. It's a more simple problem, so maybe you don't need it. But essentially, you have this wind turbine. So this blade is turning, and you can make a little circle here to show the path that this blade is going to rotate on. Okay, so in other words, when we say the radius, we mean from the center right here to any point on that circle that I sketched. Let's just pick that point right there. And so that guy, that radius is going to be 35 feet. Now coming back up, we are specifically asked to find the linear speed in feet per minute, okay, of the wind turbine blade. So what I want to do is start off by just finding the angular speed. So that omega, so let's put omega is equal to your theta, which again is in radians, over t, which is the time. Now, the information we're given here is that it makes 360 revolutions per hour. So let's think about that for a second. If I'm rotating one time around, the angle measure is going to be 2 pi. Well, it tells us we have 360 of those revolutions or rotations or whatever you want to say. So if I have 360 complete rotations, the angle measure that I'm generating is 2 pi times 360. So let me erase this and just put 2 pi. Again, that's for one revolution or one full rotation times 360 because there's going to be 360 revolutions. Now, the time here is going to be in terms of 1 hour. Okay, so if you did the math here, you would have 720 pi radians per hour. Okay, now there's one other thing I want to do. We are asked for feet per minute, and right now this is in terms of hours. So we know that there are 60 minutes in 1 hour. So in 1 hour. So what I can do, let me actually abbreviate this so it's easier to fit. I will put 1 hour up here in the numerator, and I will put 60 minutes down here in the denominator, and I will just cancel this with this, so the hours will be gone. And then I know that 360 divided by 60, that is going to give me 6. So let me get rid of this, and I'll say that this is going to be equal to, you have 2 pi times 6, which is 12 pi. So 12 pi over, this is going to end up being 1 minute. So really, if you wanted to, you could write this as 12 pi radians per minute. Okay, so that's your angular speed. Now, what we want to do is come back up here and think about the radius. Again, this is 35 feet. And to find your linear speed v, all you have to do is take your angular speed multiplied by the radius. So it's really simple. Let me actually condense this down. I'll just bring this up here. And I'll say that v, which is my linear speed, is this guy, the angular speed, so 12 pi over 1 minute. And this is multiplied by your radius, which is going to be 35 feet. And nothing is going to cancel here. So really you just do 12 times 35, and that's going to be 420. So this gives me 420 pi, and this is going to be feet per 1 minute, or per minute if you want to say it that way. Now, we're told to approximate this and round to the nearest tenth. So let me grab this real quick, and I'll just paste this up here real fast, and I'll say this is approximately. If I do 420 times pi on my calculator, I get 1,319 point, let's go 468, or rounding to the nearest tenth. So I would think about this 6 here, and the 6 falls in the category of 5 or greater. So I'm going to get rid of these and add 1 to the 4, so this becomes a 5 here. So it's 1,319.5 feet per minute. Okay, so that's going to be my answer here, rounded to the nearest tenth. Okay, let's take a look at problem number 4. So here we have the propellers on a Cessna small passenger plane have a diameter of 8 feet. At full throttle, the propellers turn at a rate of 9,000 revolutions per hour. What is the linear speed in feet per minute at the tip of the blades? Round your answer to the nearest tenth. So we want to find the linear speed in feet per minute at the tip of the blades. So again, we come down here, I have a little drawing, not necessary for this problem. Maybe that's a little too big. Let's resize this down just a little bit. So you'll notice that this from right here to right here, I've labeled that with 4 feet. In the problem, it gave us the diameter. So if you have the diameter, you need half that amount to get your radius. So this length from here to here is 4 feet. Now coming back up, if you want to start by getting your angular speed, well, here it says they turn at a rate of 9,000 revolutions per hour. Now we want to end up with minutes, right? Feet per minute. So let's come down here. And again, for omega, this is equal to your theta divided by your t. Again, 1 revolution is going to be 2 pi in terms of the angle, and you have 9,000 of those. So this is going to end up being 9,000 times 2 pi. Let me get rid of this. And that would be 18,000 pi. So 18,000 pi is what you're going to have there. And the time, again, this is in terms of 1 hour. But we want to put this in terms of minutes. So we know already that the relationship between minutes and hours, it's going to be 60 minutes is 1 hour. So let's go ahead and say that this is times. I'm going to put 1 hour up here over 60 minutes down here. And you could abbreviate both or abbreviate one, just whatever you need to do. Just so it fits, I'm just going to abbreviate both. And so this is going to cancel here. And so really you just do this on your calculator, 18,000 divided by 60, and that's going to give you 300. So let's go ahead and say this is 300 pi. So 300 pi over 1 minute. So over 1 minute. So basically this is 300 pi radians per minute. So you could put that over here like this and say this is 300 pi radians per minute. Now, if we want our linear speed, again, all I have to do is take the angular speed and multiply by the radius. The radius is 4 feet. So I think just by eyeballing that, you're going to see that it's going to be 1,200 pi feet per minute. But let's go ahead and do this more formally. So I'll say that V is equal to 300 pi over 1 minute times, we'll do 4 feet. So this is 1,200 pi, and then we'll say feet per 1 minute. So what is this approximately? Let me just do it here versus doing it on the next page. Punching that into my calculator, I get 3,769 point, let's say 9111. Now I want to round to the nearest tenth. So I want to look at this digit here. That's in the hundredths place, and that falls in the category of 4 or less. So basically, you can just cut these off and leave the 9 unchanged. So it's going to be 3,769.9 feet per minute. Okay, so let me copy this, and we'll just paste that in here. So the linear speed, in this case, it's going to be about 3,769.9 feet per minute. All right, let's take a look at problem number 5. So here we have at the local fair, Jacob is trying to win a rock toss contest. we have that contestants must place the rock in a sling and whirl it around before releasing. Jacob determines that the rock must leave the sling at a speed of 60 feet per second in order to win. Based on his arm length, the maximum radius of the circular path generated by the sling is 4 feet. What angular speed does Jacob need to obtain in order to win? We want to give your answer in radians per second, and we have a big hint here. We know the linear speed. So we are just trying to figure out what angular speed does Jacob need to obtain in order to win. So what's the angular speed? Given the fact that we know the linear speed, so that's right here, must leave the sling at a speed of 60 feet per second. So there's lots of different ways you could go about solving this. I'm just going to come down here and I drew a little image. It's not perfect, obviously, but you have a little slingshot with a rock here, and this is going to trace out a circular path. And I realized that this is not looking like a circle. It looks like an ellipse. And the reason is if you draw a circle and then you flip it to give yourself a little 3D perspective, well, you're going to end up with something that looks like an ellipse. So this is supposed to be a circle. So this guy right here, the radius is 4 feet. Now, we know that the linear speed, so when this guy leaves this right here, it's traveling at 60 feet per second. So you can put V is equal to 60 feet per 1 second like this. Now, there's lots of different formulas you could use. I think the simplest way to do this is to think about the fact that your V, your linear speed, is S, which is the arc length, divided by your T, which is your time. So we can say here that the arc length would be 60 feet. So let's say S is 60 feet. Now we're also given the radius here, which is 4 feet. So let's put R is equal to 4 feet. Now, if you have your arc length and you have your radius, then you have your angle measure, theta, in radians. So we'll go ahead and say that theta is equal to S over R. So S over R, which is 60 feet over 4 feet, which the feet are going to cancel out, and you're just left with 15. And this is in terms of radians, okay? So let me get rid of all of this. We don't need anything anymore like that. And we're just going to write out that theta is equal to 15, and let's just go ahead and put radians for completeness. And then if we think about our formula for angular speed, omega, again, this is going to be theta over t for time. So in this case, the time is just 1 second. So really, I could just plug in 15 radians here and then plug in 1 second here. So your omega, one more time, is just going to be 15 radians per second. So a real easy problem to solve. So we'll just come up here and just answer this in line. So I'll just say omega, which is the angular speed that Jacob's going to need to obtain in order to win. This is going to be equal to 15 radians per second.